All right, let's dive in. Today, we're cracking the code on one of the most fundamental ideas in all of chemistry, acids and bases. And trust me, they are absolutely everywhere, defining the world around us in ways you might not even realize.
Okay, so let me just kick this off with a question for you. What in the world do lemons, car batteries, and ant stings all have in common? I know, it sounds like a weird riddle, right? But the answer is this shared chemical identity that we are about to unpack.
So, to answer that, we've got to start with the basics. What actually makes an acid and a base a base? Let's break down what their real job is, chemically speaking.
At its heart, it really all boils down to one tiny particle, the proton. Just think of it like a chemical game of catch. Acids, they're the pitchers. They're the proton donors. And bases, they're the catchers. They are the proton acceptors. This one simple exchange is literally the foundation for all acid-base chemistry. Okay, let's get a little more specific with acids. An acid doesn't just give away a proton willy-nilly. When you dissolve it in water, it releases these positively charged hydrogen ions. We call them H+ ions. And that flood of H+ ions, that's what gives acids their classic properties, tasting sour or being able to corrode metals. And when an acid meets its opposite, a base, they cancel each other out to form just plain old salt and water.
And here's the other half of the dynamic duo. A base is all about its ability to accept those protons that acids are so eager to give away. Its whole mission is to find an acid, neutralize it, and, like we just saw, create that same simple combo of salt and water. They're just perfect chemical opposites.
But here's where it gets more interesting. It's not some simple black and white world. Not all acids and bases are created equal. Nope, there's a whole spectrum of strength, from stuff that's dangerously corrosive to things that are perfectly safe to eat. A strong acid is what I'd call an all-in chemical. The moment you put it in water, it completely breaks apart or dissociates and releases every single one of its available protons. There's no holding back. It is a one-way commitment to donating those protons.
Now, a weak acid, that's a whole different story. It's way more cautious. It only partially dissociates. So some molecules will give up a proton, but others will hang on to theirs, and the reaction can actually go in reverse. It's less of a final decision and more of a constant back and forth. And hey, this is exactly why the weak acetic acid in your salad dressing adds some flavor without dissolving the actual bowl.
And this slide right here shows that difference perfectly. The real key? It's all in the arrows. For the strong hydrochloric acid, HCl, you see that single arrow pointing right. That's a one-way trip to becoming ions. But look at the weak acetic acid. That's the stuff in vinegar. It has two arrows pointing both ways. That shows the reaction is reversible. The molecules are constantly breaking apart and then getting back together. All right, now that we've got the whole strong versus weak thing down, let's clear up a really common point of confusion, the relationship between a base and an alkali. So let's just ask it straight up. Are these two words just different ways of saying the exact same thing? Well, the answer is a hard no, but the distinction is actually pretty simple. This Venn diagram makes it crystal clear. Think of bases as the big overall category. That's any substance that can neutralize an acid. Alkalis are just a special little subgroup inside that bigger category. So the crucial point to remember is this. An alkali is simply a base that can dissolve in water. That's it. So all alkalis are bases, but not all bases are alkalis. Okay, so we can define them, we can categorize their strength, but how do we actually measure it? Well, for that, chemists have a really simple and elegant tool, the pH scale.
And here it is, the universal ruler for acidity. The pH scale runs from 0 all the way to 14. Right there in the middle, at a perfect 7, you have neutral. Think pure water. Anything below 7 is acidic, and the lower the number, the stronger the acid. Anything above 7 is alkaline, and the higher the number, the stronger the alkali. Simple as that.
So how do we find out a substance's pH value? Well, you've got two main ways. Over on the left, you see a universal indicator. You just add a few drops, the solution changes color, and that gives you a quick visual ballpark. But for more precision, you use the tool on the right, a digital pH meter. That thing will give you an exact numerical reading right down to the decimal point.
And finally, let's get to the chemical payoff. Knowing all these definitions is great, but the real power comes from being able to predict how acids will behave. Turns out they follow a few key rules, which makes the reactions powerful and, more importantly, predictable. This table lays out the 4 fundamental types of acid reactions. Now take a second and look for the pattern here. You notice it? In almost every single case, the first thing you get is a salt. What changes is the other stuff that's produced. For example, when an acid reacts with a metal, you get flammable hydrogen gas as a byproduct. When it reacts with a base, that classic neutralization we talked about, you just get water. And with a carbonate, like limestone, you get both water and carbon dioxide gas. In fact, that's the reaction that causes acid rain to slowly dissolve statues. Understanding these patterns is everything.
And that brings us to a final thought. We've seen that the story of acids and bases is really a story of opposites, of giving and taking, all aimed at finding a balance. So it makes you wonder, right? Where else in the natural world do we see this exact same principle, this neutralizing balance between opposites at play, just to keep a system stable and functioning? It's a question that takes this chemical code way beyond the lab.